if it were flying free, it would take a photon initially created in the deep core of the sun about 2 seconds only to travel to the surface. Then it would take that sunlight another 8 minutes to reach us here on Earth. Now in reality, that first part doesn't happen. Why is that? Now in the clip you're about to see, we explain this by considering a photon's random walk through the sun. The clip is from the course I'm teaching at my university in Radiative process in astronomy. I should point out 2 things. And the first thing here is that the concept of a mean-free path I'm talking about, that's simply the average distance the photon travels before it interacts with, in this case, the stellar material. Now, the second thing is that a significant part here is actually spent to try to get an intuitive understanding of the so-called square root of n law of statistics. And this is since I found that very often this is just taken for granted without further motivation when this example is given. The star as an example, we could have also taken a very optically thick accretion disk or the other astrophysical media of interest, right? But of course, the sun is just there, so it's easy to take it as an example, so we're going to do that again. All right, and then we're interested, okay, but what is this mean-free path of a photon now, right? Typically in the sun. And to do that, it turns out that this description with kappa and rho is a convenient way because we can do a simple order of magnitude estimate. This is not exact, it's just to give you a feeling for it. Okay? So for that we need some sort of average density of the sun, so we can just take that the average density of the sun times the volume of the sun. It's a sphere, right, with some sort of radius. That's going to be the mass of the sun, okay? So in this sense, the order of magnitude average density of the sun is just its mass divided by its radius cubed and some numerical factors of order unity, or a little bit more or a little bit less. Yeah, this is 2 times 10 to the 33 grams. If I'm wrong, somebody correct me. This is 10 to the 10 centimeters, I think, like this. The point of this, of course, this is 30, and there you get another 2. So this is just on the order of 1 centimeter, a little bit more perhaps. But we also had some 4 factors there, which we neglected. 1 grams per centimeter cubed, right? Now, kappa nu, we would have to calculate, so I'm just going to give you that for now, right? The reason why kappa nu is a convenient, one of the reasons it's a convenient measurement of opacity, right, is that, well, a typical value here would be 1 centimeter squared per gram, okay? That's not the case for extinction, for example, alpha. So the mean-free path then becomes, well, you know, 1 over 1 times 1 in CDS units. So on the order of 1 centimeter. Again, this is an order of magnitude estimate. It's not intended to be precise. It's just intended to show you that on average, the mean-free path inside the sun of a photon is really, 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 really low. It's actually, if you go to the core, because the density increases so rapidly toward the core in the sun, it's actually even lower close to the core. Yeah, so this is a little bit an overestimate. So, but then you can think, okay, we had this diffusion process, right, of energy, and now we're again going to assume that that's how photons come through this whole region, released from deep inside the sun, and then they're going to diffuse outwards until they reach this boundary layer and then they're going to escape to us, and they're going to reach us 8 minutes later, because that's how long it takes for them in free streaming from the surface of the sun to us here on Earth. But then what's going to happen, of course, is that they're going to be constantly absorbed, re-emitted, scattered around, etc., all with like a distance of 1 centimeter. Yeah? But the radius of the sun is very, very big. So it's going to be something like this. I can't. And then, you know, some are going to be scattered down there, and another one is going to be, yeah, and they're going to have a hard time getting their way up. And then perhaps, yeah, okay, and then it becomes longer and longer, and then it escapes. And some of them eventually, they're going to escape. Okay, this is what we call a random walk, a Rankin's walk, and you can ask yourself, but how on earth do they get out at all if the mean free path is so short? How can this happen? Well, think about it in this way. All right. If I'm now standing here and I do the drunkard's walk, yeah, I tilt 1 step on this, and I can only tilt in this direction now. That's going to be easiest, right? I tilt in this, and then it's 50-50 going there and there, right? Then it's here, and then I can tilt there, and then 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 there, and soon I'm going to be out of sight here, right? Now soon I'm out of camera in the video recording. In the classroom you can still see me, yeah? But I'm actually, if we think about this as the edge, then I'm now out of the edge, right? The thing is that when you describe this process, you can also do it, you know, if you're I don't know, if you've been at Audemarkt and you're going to walk randomly to the classroom on a Friday morning or something like that, then you can say, what's the probability of me actually in a certain amount of time hitting the classroom? Well, it's not so high, because then you, of course, have the two-dimensional surface. But if you only calculate the distance, then you can sort of say tilt the distance, and then if you're standing at Audemarkt, you can ask yourself, okay, after a certain amount of time, where is my friend? Will she or he be at the center, or will they more likely have tilted toward one or the other way? Okay? This is the so-called random walk. And to make it easy for us, we can just say that in this case, this is what we're interested in, we're going to either take 1 step up or 1 step down in the C direction. Okay? So either 1 step, which then is with L plus, or L up, or 1 L down. Okay. And then the average is not a good measure, because the average will come out as 0, right? But we know that the likelihood that we're actually exactly there is not going to be high. Yeah? We're going to be tilted this and we're going to be tilted that. And the whole idea here is that for some of them, we're getting so tilted that we actually reach the boundary layer and we can escape. Right? And the good measurement for this is the root mean squared. So in this case then, we can say that at the nth, yeah, we have 2 possibilities. We're either at the n minus 1, right, plus L, okay, or we have the possibility B, where we're at dn minus 1 minus L. Those are the only 2, right? And they're equally probable. We don't have a higher probability to tilt one way than the other in this example here. Then if we now calculate the mean, then we can see that this is just then going to be the NA squared plus, this is the root mean squared, right? Divided by 2, which is then just the n minus 1 plus L2 plus, the n minus 1 minus L squared, and then we're going to have to divide this by a factor of 2, right? Now, you can just look at this and you can see, okay, but that's neat because the cross terms, they're going to cancel. Yeah? And then we're going to get 2 of these out, and that's going to cancel the factor of 2. So we're ending up with dn minus 1 plus L squared. Okay, well, that's interesting because we can now just put it in this way. If we start at dn0 squared, we say that to be 0, then we see that dn1 squared is just L squared, right? Oh, no, the 1 squared, the 2 squared is just then 2L squared, and the 3 squared is just 3L squared, and so forth, until the n squared is just going to be n times L squared. So the root mean square average, the n squared, is just going to be square root of n times L, where L is your mean free path. And this is, of course, the square root of n law that you may or may not have seen in your statistics course. So did this have anything to do now with photons escaping the sun? Let us think a little bit about that, because I'm pretty sure it did. Okay, so that's a good measurement on how far we are now from the core. So if we now have again our random walker, and we're interested in then reaching the boundary layer here, which is some distance d, then we want that distance d now to equal this square root of n times L, because we want it to be the root mean square distance. Now, another way to say this is that if we have n number of scatterings, absorption, re-emissions, that's going to be d squared divided by L squared. Okay. So now, what time can we associate with this? Well, that's a random walk time. Well, that's sort of, if we now again put ourselves into this, what is the random walk time? Well, in one of this, it takes L, right? So L times the number n, that's going to be the time times the speed of light c, because that's how it goes in one of these. So that's just going to be L times n. So the random walk time in this case is just going to be Ln divided by c, or if we put it into this, we can see that it is d divided by c times d divided by L. Or if we put this in the, for the sun, it would be the radius of the sun divided by c times the radius divided by L. Now, the first here we recognize as the free flight time, right? And the second term is the enhancement factor. The free flight time here is how long time it would take the photon if it were just freely escaping from where it was initially created, released, and then just out here. right? That's the free flight time. We can calculate this for the sun in a simple way. That's just the radius, which we know is 7 times 10 to the 10 centimeters. The speed of light we know is 3 times 10 centimeters per second. So this is just on the order of 2 seconds. So it would take the photon roughly 2 seconds if it were free streaming. Now let's see how long time roughly it would take for it to actually diffuse out. So that's going to be times this enhancement factor. We already calculated this to be on the order of unity. The radius, the order of unity in the sense that it was a centimeter. The radius of the sun we have there. So this is enhanced by a factor of roughly 10 to the 11. So this is on the order of 10 to the 11 seconds, which is on the order of 10 to the 4 years. Again, these are order of magnitude estimates. You could do a more detailed calculation of this. Come out a little bit higher. The point is that it takes thousands and thousands of years for when the energy is released down in the sun, diffuse outward to the surface, and then it goes out by means of this random walk process. Yeah? I am trying to avoid to say that it is the photons that are created in the core here, and then they're scattered around and then escaping, because technically. So that was pretty cool, right? So when you go outside and look toward the sun today, think about that. The light that you see reflects the conditions in the deep solar core as they were many, many thousand years ago. Ancient starlight. Or well, I sort of hinted at some caveats already in the video that we just saw, which I just wanted to follow up upon toward the end here. Let's compare to a super simple simulation of a random walk that you're seeing on the screen now. Now, these are not drunk ants. It's a Monte Carlo simulation showing a simple random walk where I set the mean free path to a fixed fraction of the sun's radius, namely 5%, or 0.05 times our sun. But remember from the video, we estimated that a typical mean free path in the sun is on the order of 1 centimeter. And in terms of the solar radius, that would be about 0.00000000001, or about 10 to the minus 11 our sun. And of course, this is just what is reflected in the many thousands of years that we estimated the random walk travel time to be. Here we assumed that all energy transport is done by the photons, but through some parts of the sun and stars in general. Parts of the energy can also be carried by turbulent convective gas motions, so one would have to take that into account. For true absorption and emission processes, energy is constantly exchanged between the gas and the matter. So while the typical energy of the photons in the sun's interior is very large because of the high temperature there, they're going to be X-rays or so. The energy of the photons that finally escape, they reflect the conditions in the layers where the last interactions occurred. And that is typically around the sun's photosphere. Now finally, I used the average density of the sun to estimate the mean free path. In reality, the density is much, much higher in the deeper layers than it is close to the core. And this means that the photon would be trapped down there during much longer timescales. And then, once it got closer to the solar surface, it would move around more freely. Now, typically, this leads to somewhat longer timescale estimates on average than what we did here today. So actually, this decreasing mean free path is just what makes Monte Carlo simulations of photon transport kind of impractical in very deep, what we call optically thick layers. Now, the Monte Carlo technique, however, is very useful for simulating radiation transport through diluted atmospheres and winds, especially when these are dominated by scattering, as you can imagine now. But I think we'll save that for another day. For today, we had our nice analysis of our ancient sunlight.